This is section 1.5, the limit of a function. And this is a big calculus idea that comes back to us multiple times throughout the semester. So we have a very, calculus-like definition. We have a function, f of x, and the limit, the definition of a limit, is if f of x, if the function gets closer and closer to the real number L, as x gets closer and closer, but not equal to a, then we say that the limit of f of x as x approaches a is L. So all this really means is that as we get closer and closer along the function to some x value a, are we also getting closer and closer to some y value L? And when we say closer and closer, we really mean infinitely close. So the way that I talk about this often when I'm teaching it in the classroom is if you think about standing across the room from a wall, and if I tell you, okay, every time I say go, you're going to go halfway to the wall. So you're standing, say, 20 feet from the wall, and I say, okay, go. So now you're going to move 10 feet towards the wall. So I go halfway to from wherever you are to the wall. So now you're 10 feet from the wall. And then I say go. And since you're 10 feet from the wall, now you go 5 feet, and now you're 5 feet from the wall. And we can do that again and again. So I say go, now you're 2.5 feet from the wall. I say go, now you're half of that. So 1.25 feet from the wall, and so on and so forth. But the idea there is, no matter how many times we do this, no matter how many times I say go, you're never going to get to the point where you're touching the wall, because you're always going half the distance from where you are to the wall. So even if you are this far from the wall, you're still only going to go half that. So the idea behind this kind of real world anecdote is that the wall is the limit. You're never going to touch the wall, but you're going to get infinitely close to that wall. And that's kind of the big idea behind a limit, is that you don't actually have to touch that thing. That thing, like even if the wall wasn't there, right? I could have some invisible barrier that you're getting closer to. The wall doesn't even have to be there to be the limit. The limit is, whatever it is that we're getting infinitely close to, whether it's there or not. So we have some notation for a limit. So this is the limit as x approaches a of f of x equals L. So this is the most common one. We don't see this one quite as much. It's more likely to see the first one, but that's how it's read. So I've already shown it to you graphically here. Basically, if we're getting close in the x direction, are we also getting close to something in the y direction? So we would say if x is real close to a, then f of x, which is our function, is really close to L. And when we say f of x, graphically, we're really just saying the y values. Are the y values close to some y value here? So as I was talking about the wall, the value of L does not depend on whatever that value is, f of a. So what that tells us is you could have a limit where the value at that limit does not actually exist. And we'll see pictures of this soon. So if we think about this question here, which is the limit as x approaches 1 of 2x squared plus x minus 1, it's really just asking us, if you think about this, this has a y-intercept at -1, and then we're here. So the idea here is that this parabola goes up on one side, and it goes up. We know there's symmetry, so it goes up on the other side. Okay, that's not perfectly symmetrical, but you see what I'm saying. So our job is basically to find out what happens as x gets very, very close to 1. And so really, because this is a parabola, it's smooth and it's continuous. Like the domain is all real numbers. So what that's telling us is that every time we put in an x value, out will come some real y value. But in order to estimate using numerical methods, because that's the first thing we're doing essentially, this plug and chug. So all this is telling us is take the 0.5 and plug it in to 2x squared plus x minus 1. We're choosing values, as you can see as you go along, choosing values that are getting closer and closer to 1. This is over here, as you should notice, coming from the left-hand side. And this over here is coming from the right-hand side. So we're getting closer this way and we're getting closer this way. And we're seeing what happens as we get close this way and we get close this way to x equals 1. So if you want, you can pause and take a few moments, use your calculator, and put in these values into 2x squared plus x minus 1 and see what value comes out. Understand that that's the y value on the graph. We put f of x here because we're calling it, this function f of x. So if you put in 0.5, all we're saying here is that, I'm not going to do all of them this way, but you're putting in 0.5, you're squaring it, multiplying by 2 plus 0.5 minus 1, and you're seeing what comes out. So the first value that comes out should be 0. And then again, if you want to pause and do these, go ahead and do that, and then come back and you can check your answers and make sure they're right. Being able to do this is important, and depending on what kind of calculator you have, it can kind of go faster or slower. Okay, so these are the values that come out when we put in those values for x. So you can kind of see, because the whole idea about estimating is taking a look and saying, are we getting close to some number? And if you notice, it looks like we're getting pretty close to 2 from the left-hand side. Now let's put in the values from the right-hand side. So again, you can go ahead and do this if you want, and then check. So if you're not getting these numbers, there's probably an issue with how you're doing your calculator, so definitely get that checked out. So you can see that coming in from the right side, we are also getting close to 2. But notice when we're 0.5 away, our number's really not close to that. So we got to get really close to 1 on either side in order to get something that's pretty reasonable. So what we're seeing here is that the y values are getting closer and closer. Hopefully you're seeing that they're getting closer and closer to 2 as the x values get closer and closer to 1. So that's the idea behind this, kind of estimating using this idea of picking values that are close to the value that you're approaching, in this case x equals 1. Now here's another example. Notice it's a little bit more. We've got a higher level polynomial here on the top. We've got a binomial on the bottom. This together, don't forget, creates a rational function because we have a polynomial on the numerator and the denominator. Now we're also approaching x equals 1, but if you're really on top of it, you will notice that in the denominator we have x minus 1. So if we were to just plug in 1 to this, we'd have a denominator of 0. Now you might be thinking, so does that mean we don't have a limit? But we want to remember that it doesn't matter if there is or is not a value at 1. You can say there's nothing at 1, like we can't have a y value at x equals 1, and still have a limit. Like it is still possible to have that. So let's try using numerical methods, see what happens. So we have the same x values here, so this is a different function, but I'll show you what happens when we plug in the y values. Again, you can check these. You're probably looking at that polynomial and saying, I don't want to plug those in. But if you try 1 or 2, just make sure you can get the right answers. That would be very smart. So we get 0, we get 2 point. Ooh. Sorry, they gave me a tablet that's like the size of a deck of cards, so I'm still getting used to writing with it. It's teeny. Okay, and then we have this. All right, so we see maybe not quite as quickly, but as we are getting close to 1 in the x direction, we are getting close to something in the y direction. You can probably see what that is. And then we'll do the same on the other side. Here we get a value that's way out there. Here's the other ones. And as you can see, again, takes a bit more time, but it does look like we're getting close to a certain value. And of course, we could put in 0.99999 or 1.00001. We could get infinitely close to 1. And hopefully what we would see then, of course, is getting closer and closer to some certain value. So on the basis of this information, all we have, of course, is this kind of complicated polynomial on the top, and then the bottom, this rational function. We would estimate, hopefully, and you see this as well, that the limit is 4. So again, idea of numerical methods is just plugging in values close to what you're approaching and seeing what happens. So at the top, take a look at the note. The limit of a function may exist at a given x value, even if the function does not exist at that value. And that's what we saw in the last example. We can't plug in 1 because 1 requires us to divide by 0. No matter what's in the numerator, you can't have 0 in the denominator. And so because of that, we might have thought, oh, there can't be a limit. But in reality, using numerical methods, we actually see that there is a limit in that case. So now we have find the limit as x goes to 0 of e to the x minus 1 using numerical methods. And the denominator has 2 times sine of x. So a little more exciting here. What I want you to notice is that e to the 0 minus 1, what's e to the 0? What's anything to the 0? 1 minus 1, we get 0. And sine of 0, you may or may not remember, but sine of 0 is 0. So in this case, by just plugging in 0, this x value that we're trying to get close to, we get 0 over 0. That's a big problem. So again, we might think, oh, there must not be a limit. But by just using numerical methods and getting close, we're going to try. So think about what values we want to choose, because now we're not approaching 1 anymore, we're approaching 0. So we're going to have 0.5, and then think about what else we could do. 0. And, there's different options here, but obviously your goal would be to try and get as close as you can to that value. So now we haven't seen this yet, but if you think about the other side of 0, now you're talking about negative numbers. So in some ways it's a little bit easier because you can choose the same values that we just chose, except the negatives. But of course it does mean that you have to plug in negatives. And so that can be a little trickier, right, depending on how good you are with your calculator. So do make sure you're in radians if you're using your calculator here and testing some of these values. You want to make sure that your calculator is doing the numerator by itself and then dividing by what you have in the denominator. That's kind of a key thing. So make sure that you can either use a fraction bar or parentheses to make sure your calculator is doing the right thing. So the values here are pretty involved. They're not quite as easy as the last ones, but give me a second and I'll write them out. And again, make sure to check a few of these and just make sure you're getting the same numbers so that if you have to do it on your own, which you will, that you can do that. Ooh, really got to figure out this tablet. And so here's coming in from the right-hand side towards 0, the positive side coming in from the right-hand side. We're seeing these values. So as you can see, it does look like we're getting pretty close to a 0.5 in the y direction. Let's see if that's the same in the other direction. Here we go. So as we can see, coming in from that negative side, doing something like a negative e to the negative 0.5 minus 1 over sine, put the 2 over here, sine negative 0.5, you're going to get this lovely decimal here. But we can see as we look from both of those sides that we are in fact approaching, from what we can estimate and tell, the same number. And we can see that that is about 0.5. That's what it looks like to us anyway. So that's the same as 1/2 or 0.5 either way. But realize that we need to do it that way because, if we were to just plug in 0, we're going to get 0 over 0. That's not something that we can define. And so using this numerical method of getting close is something that actually allows us to do an estimate of this limit. Okay, so this is just a short video on the graphs that we've just been seeing. And so the first one we mentioned, it was a parabola, and it's just a normal quadratic. And we were looking at the limit as x approaches 1. So what we see here is as we approach 1, from the left-hand side and from the right-hand side, we are in fact seeing that we approach 2, the y value of 2. As we come in, notice we go down, coming up, we hit that value of 2. So it makes sense to us using the numerical methods that this is what we get. Because quadratics are smooth and continuous, we see, sure, as we approach 1 left hand and right side in the x direction, we're approaching 2 in the y direction. Now for the second one, we had that really kind of 4th degree polynomial divided by a binomial of degree 1. And in that case, we have a function that looks like this. So what I want you to notice is this looks pretty smooth and continuous, except there is a hole. And from pre-calculus, students should be aware that what this means is that the numerator and the denominator have a factor of x minus 1. So of course the denominator has a factor of x minus 1, but so does the numerator. And so that means that essentially it's a hole because it's just this x minus 1 in the top and the bottom that arguably could be simplified, but they're not, right? They're in the function. And so it creates this hole, but just at that value. So if we were to just plug in 1, we're going to get 0 over 0. But if we looked at that numerical method like we looked at, as we put in the values close to 1 on either side, coming in from the left, coming in from the right, we're approaching 4 in the y direction. It doesn't matter that there is no value. It doesn't matter that there's a hole there. We can get infinitely close. We can put in any value at all that is close to 1 on either side, and we will come out with a real number value. The only value we can't put in is 1. But that's okay, because a limit is about what you're approaching and getting infinitely close to, and not what the value is there, if it's there or not. And then the last one was this kind of crazy e to the x minus 1 divided by 2 sine x, and this is similar. This has this discontinuity, is what we're going to call it. We'll learn that later, just at that 0. And so we can't put in a value at 0. We get 0 over 0. However, it is just a little hole there. There's going to be other ones in this because, of course, sine has multiple places where it is 0. So you'd find it other places. But just thinking about the fact that we were approaching 0, you can see that as we approach 0, there are values. There are plenty of values there. But we can't plug in 0. But we can tell that by getting infinitely close, that we're going to approach 1/2, which is what we found numerically. So, using programs like Desmos and such, getting an idea of what these functions look like can be very helpful when you're thinking about limits.